You know what really grinds my gears? Duckweed. Duckweed is so annoying. So duckweed's this little tiny plant that gets into aquariums, and it's great. It sucks up a bunch of nitrates, but it gets everywhere. I know this because I have aquariums at home. And guess what we're going to use as our spark on learning? So we are on section 9.2 called graph logarithmic functions. And hey, look, duckweed. It's crazy. This plant grows by dividing. So if you have 4 plants, that could turn into 8 plants, turn into 16 plants, so on and so forth. That sounds like one of our exponential type curves. So duckweed ranges throughout the United States. Get out of here, face. And is very common in the aquarium trade. Although it's very common in nature, it is also grown commercially as animal food for bioremediation and even a possible source of biomedicine. So here's where it kind of relates to what we're talking about. Under ideal conditions, duckweed can approach exponential growth. Again, because it divides and stuff. So research plan to grow duckweed until its fronds cover a given area. What is a mathematical question you can ask? Well, of course, what is the actual equation of the duckweed growth? So how much do they start off with? And so here we go. Research began with the duckweed that covers 1 meter squared and want to grow enough to cover 50 meters squared. And so we've got our equation. T is in days. And so how long would it take? So this is just another application of some of these exponential curves and logarithm curves that we are learning about. So let's graph these things, shall we? So hopefully some of this is going to sound familiar. Graphing logarithmic functions. So just like our exponential functions, logarithmic functions are going to have parent functions. And then these parent functions can then be translated up, down, left, right, squeezed, stretched, whatever, into whatever function we're actually looking at. So our log functions the parent function is going to be log base b, so that b is what's going to change. So for example, we have already seen log base 2 in some of our previous examples, right there. So here's our graph for log base 2. This would be our parent graph for log base 2. So logs of different bases, you need to know it, but the 2 most common things that you are going to see both in mathematics and the real world is going to be log base 10. Remember, when there's no number there, it's assumed to be 10. And log base e, otherwise known as natural log. So first things first, compare and contrast the graphs of the parent logarithmic functions with base e, f of x equals log of x, and base e, f of x equals natural log of x. So instead of using the graphing calculator function, I used Desmos because I just think the graphs are prettier. And move my face over here or down here, whatever. So my red function is going to be log of x. My blue function is natural log. So let's use our graph to answer some of their questions. So we come over here. So this is our f of x over here. This is our x. So when does our f of x equal -2? We can look over here. Our -2 is at 0.01. So 0.01. For some reason, the program is not letting me do any of this stuff correctly. So this one's going to be 0.01 right here. So then our -1 is going to be 0.1. And then 1, 10, let's check 2. Whoops. when is this red line going to cross 2? That's really big, isn't it? So you can see that the x values here are dramatically increasing. So this would be 100, and this would probably be 1,000. All right, now we got to do the same thing for our natural log of x. So it's going to be our blue line. So notice how it increases a lot faster after x equals 1. But let's look at our table. So again, it's not letting me drop things up there. But if we look at our natural log at -2, we're going to come all the way down here. It's that weird number. Well, that number is actually 1 over e squared, -1, 1 over e, 0 and 1. And then you're probably going to notice the pattern. E is e squared, e cubed, so on and so forth. So there's our table with that. And so this is talking about what can you see from the tables in the plotted ordered pairs of the graph of f of x log base 2. So that's this guy, remember. So we're talking about just the, what were they talking about? So just the range values, so the y values, -2 to 3. So from -2 to 3, you see it's this part of the curve. When we look at our log base of x, again, -2 to 3, so that's our red line. -2 is down here. 3 is going to be way over there on that part of the graph. I guess more off the screen. So that's going to be up at like x equals 1,000. And then our natural log, you can still see almost. We'll zoom out a little bit. X equals 3. Or I guess, I'm sorry, y equals 3 is up over here. So what do these domain values indicate about the relationship of x and to the base, and what scale you would need to use on the x-axis to graph the logarithmic functions? So if you guys are graphing logarithmic functions, this is kind of good to know about the scale of what you guys need to set your windows on your calculators. So you would need it to use a larger scale for the larger values, or extend the graph much further to the right as b increases. So as the log, remember b is this one right there, as that gets bigger, you're going to need a lot bigger of a graph to actually see the different things. As the base increases, b greater than 1, the third power of the base, which is the domain value corresponding to the range value of 3, increases. So that is, again, relating the parent function of the different base values to actual b. And we'll see that a little bit better next time. Or a little bit later, sorry. What do the three functions have in common regarding their range values as x decreases from 1 towards 0? They all decrease in an unbounded way. So they're all kind of approaching the asymptote of x equals 0 in an unbounded way. So they all kind of look somewhat like that. How does the relationship move? We're not doing that one. So you can, if we're going to talk about end behaviors here, so you've got an end behavior as x approaches positive infinity, but as x approaches negative infinity, you can't really talk about that because all of this past the x-axis is undefined. So just to put that in perspective, here's our graph of whichever one. This is just a generic graph. So everything over on the left side of the y-axis is undefined. So there is no such thing as what is the end behavior as x approaches positive infinity. Undefined, you know. So we can be a little bit more specific about how it approaches 0. So as x approaches 0 from the positive direction, so again, what that means is as x approaches 0 from the right, so going this way, and then we can also talk about as x approaches 0 from the negative direction. So there we can talk a little bit more. So as x approaches 0 from the positive direction, or like the yellow line here, we can say that it approaches negative infinity. Y would approach negative infinity. And then from the left is all undefined, so you're not going to have anything. So the mathematical terms that they had were all of 3 of the graphs decrease right here in an unbounded fashion. So that's what they're talking about. Okay, let's actually get into it. So if we have our parent graph, just like we have in our exponents and all of our other graphs, we can have transformations and we can graph based on our parent graph and a little bit of information. So recall with our exponents, our exponential growth functions, we had 2 reference points that we used. So we used, recall the reference points 0, 1, and then 1b to help you graph transformations of parent functions of exponential functions. So here we're going to use similar things. So except since we're doing the inverse, this is going to get flipped around. So our reference points, here's our wonderful graph, or a chart. So our reference points, we're going to use 1, 0, and b0. So whatever that base is, right there, that's going to be part of our reference points. And so here we've got our generic function, our reference point 1, and our reference point 2, and then those asymptotes are going to be super helpful as well. But here, remember, our asymptotes are x equals as opposed to y equals. So let's try it out. Let's see, do I want to write that on the screen? Sure, why not? So we're going to say, we'll put up here, g of x equal to a log base b of x minus h plus k. And I'm hoping that we're kind of getting used to this process here because we've done it just same process for just multiple different types of equations. And so our reference points are going to be 1 plus h, k, and b plus h, a plus k. And then we'll have our asymptotes. So when it says graph g of x equals 3 log base 4 of x minus 2 plus 8, we should be able to figure that out based on all of our stuff. So first things first, we got to identify our key parameters. So we've got our function up here. So just based on that, we can say our a is equal to 3. Our b is equal to 4, right there. Our h is equal to positive 2, even though it has a minus 2, but remember our generic function has a minus as well. And then our k is equal to 8. So from that, we can gather things like a equals 3. It's a vertical stretch by a factor of 3. That's going to be hard to see, so that's why we have reference points. H equals 2. That means that's going to be translated up 2 units. So the asymptote's going to, I'm sorry, no, not the asymptote, not in this case. But our reference points are going to move up by 2. I'm sorry, to the right 2. So H is going to move left and right. So that will move our asymptote. And then k is going to be translated up 8 units. That will not move our asymptote. Sorry for the confusion there. Why is h equal to 2 and not negative 2? We already talked about that. So find the reference points and the asymptote of the parent function for g of x. So with all of this information, we should be able to plug it into here. And so we would know that our first reference point, I'll do it on the left, is 1 plus h. H is 2. So we're going to have a 3 there. And then k is 8. And then our second reference point is going to be b plus h, 4 plus 2, a plus k, 3 plus 8, which equals 6, 8, 9, 10, 11. So is that what they got? How can you find the coordinates of the second reference point? By subbing in b and h, a and k, b equals 4, a equals 3. Let's see here. Second reference point. We can also, let's see here. So that one's wrong. Find the coordinates of any points and adding 2. Yeah, I didn't think so. So the other way of doing it is by translating 4, 1, which is our first reference point. I'm sorry, not our first reference point in this one, but a reference point of the parent function, and translating it up, whatever it said, 2 units to the right, and then translating it up 8 units. So that's 2 ways to do it. I feel like this way is kind of harder, but whatever. I love my algebra, so that's why I'm going to keep doing it. So graph the transformed function. You're going to graph these 2 points right here and right there. I should probably use a different color so that it stands out a little bit. You got your your 2 reference points, 3, 8, 6, 11, and then you've got your asymptote at x equals, what, 2, right? Is that where our asymptote is? Yeah. So then you can use that to then graph your function here. So that's how you're going to graph these things. So the unlabeled point on the graph of f of x equals log base 4 of x above has a coordinate 16, 2. How can you verify that? The unlabeled green point on the graph of g of x is this image. So what you could do, so this point would correspond to this point, and you would start with this point and then do the transformations, up how many units, over however many units, and you can verify that this is the image. So when they say it's the image, it's the corresponding point to your parent function. So that's what they mean by that. 3. So we are still graphing the logarithmic functions. This is kind of a real-world example. So the velocity of a flying bat involves many factors, including wing beat frequency, aka how quickly a bat flaps its wings, and amplitude, the angle at which wings flap, blah, 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 blah. Some species, the relationship between flight velocity, how fast you fly, and wing beat frequency for a bat with a mass of 10 grams, we don't care about this right now, can be approximated by, we have our function. Notice that it is a log function, where v is the velocity in meters per second, and f of v is the wing beat frequency per second. So v is how fast it's flying. F of v is how fast it's beating its wings. So we've got our equation, and use transformation to describe the graph f of v, then describe the relationship shown over the appropriate domain for the model, which is approximately 2 to 10, including 2 and 10. So let's go ahead and write that generic function up here at the top. Remember, that's g of x is equal to a. In this case, it's log base 10, so it's just log of x minus h. That should be an h plus k. So then we can analyze our function a little bit here, and we can come up with some things that it means or whatever. So we first look at this number. So that means that our a is going to be equal to -3. We can then look at this number. So v is the same as v minus 0, which goes along with that part of our function. So that means that h is equal to 0. And lastly, we've got this plus 12 goes along with plus k. So that means k equals 12. So now that we have all that, we can start talking a little bit about what the actual graph is doing. So let's see here. We got a vertical stretch by a factor of 3 reflected across the x-axis. That's because it's negative. K, we got a vertical shift up, and we do not have a vertical shift left or right because our h is equal to 0. So algebraically, we can find the reference points. So because I totally have those memorized. Not. So our first reference point is 1 plus h. That's not right. 1 plus h, k. And then we have b plus h, a plus k. So we can use those to find our new reference points. So since it is a log base 10 function, our reference points of our parent function are 1, 0, and 10, 1. It's not something you necessarily need to find the next reference points, but it's good to know. So our first reference point, we'll go blue, is right there. So that's going to be 1 plus h. So that's going to be 1. And then k is 12. So notice how that's the same thing they got. Now they're doing this whole thing here because they're using every bit of information. So for example, they're saying, you start with this point, you do a vertical shift with it. I'm sorry, not a vertical shift, a vertical stretch with it, and then you add the 12. And that's all well and good, but ultimately, because our initial reference point is 1, 0, it's still always going to be that. So you can just use this formula right here and be done with it. So I'm personally not sure why they go through, but they're probably just trying to show you that they are using all versions of the information. So then second reference point, b plus h. So our b, in this case, since it's a regular log, is 10. Remember, when there's no number there, it's log base 10. So it's going to be 10 plus h, which is 0 in this case. And then we've got a plus k, so that's -3 plus 12. So we've got 10, 9. So here's our first reference point, here's our second reference point. So then we can start answering questions as well. So why does the asymptote not change? So if we think about the graph of this, So it was vertically shifted, but it was not left or right shifted at all. So remember with logarithms, the parent function is something like this. So if it moves up or down, you still have an asymptote at x equals 0. So even if you shift up, that's still not going to affect the asymptote. So what is it? The graph is not affected in the x direction, which is true, but it is affected in the y direction. That's true. The graph is not affected in both directions. Ooh, I can check it. Yay, good thinking. So use the coordinates and the reference points to graph the parent function. You can use a calculator to find. So they kind of did that part for us. So I would just shove this into a calculator and then you can be able to see it. So, you know, you can find 112. Oh no, come on, pencil. You can find 112. You can find 10.9. And so you have this graph right there. So we can erase some of this stuff. And what does all of that mean? How does the graph reveal the vertical stretch? That change in y from 0 to 1 and then 1 to 12 to 9. So that's what they're talking about down here whenever it says the change in y between the reference points for the parent graph is 1. You know, x is 1, y is 0, y is 1. So then while the change in y between the images of the image points is 3. So that's what they're talking about there. So then since f of v includes a reflection of f of x equals log base 10 of x across the x-axis, why aren't the point at 10.1 and its image at 10.9 on opposite sides of the x-axis? Select all that apply. So if you think about it though, so you start here, you have a negative sign, which then flips it around the x-axis, but then you move it up 12 units. So if we come back down here, when you perform the transformation, the reflection is made before the vertical shift, like we kind of talked about. Then after the reflection, the reference point at 10.1 and its image would be on opposite sides of the x-axis, but the vertical shift then moves the image point back above the x-axis. So again, that's what they're kind of talking about. This gets flipped around the x-axis, but then gets moved up. So like this reference point would be flipped around here, but then is moved up. Analyze models involving logarithmic functions. So they're going to give us a couple of mathematical models, 2 of them specifically, and so we can kind of analyze them. So in this situation, to quantify the brightness of stars as seen from Earth, which is the thing, astronomers use a parent magnitude scale for which a magnitude of 0 represents the brightness of the star Vega. Brighter stars have negative magnitudes, and dimmer stars have positive magnitudes. The human eye can see stars up to an apparent magnitude of 6. Using a telescope increases this limiting magnitude. Long story short, the better telescope you have, the more stars that you can see. Although there are many formulas that model the limiting magnitudes of telescopes, a commonly used formula is this guy right here, where d is the diameter in millimeters of a telescope's primary lens or mirror, and ml is the limiting magnitude. The smallest telescopes have a diameter of 50 millimeters, but the largest optical telescopes have a diameter of 10 meters, or 10,000 millimeters, or more. A graph of the limiting magnitude function is shown for telescopes with a minimum diameter of 50 millimeters. So if we zoom in on this graph, so we're looking at, this is supposed to be 50 millimeters right here, and this is your apparent magnitude. So as you see, the bigger diameter of lens you get, the greater apparent magnitude that you can see, which that makes sense, but there's a limiting factor here, so it's not just a linear factor, which is why we have these logs. So identify the key features of the logarithmic function. So the domain of the limiting magnitude function is 50 to 10,000, and that's because our minimum is 50 millimeters, and our largest is 10,000 millimeters. So that's our limiting factor, limiting domain. So let's see if we got the correct answers. The graph shows that the function increases, okay, throughout its domain. The formula gives ML of 50 approximately, you can look at this, 10 point something, maybe 11, 10.5, we'll go for that. And ML of 10,000, it doesn't go to 10,000. So I'm looking down here, and it only goes up to 400. I think they have another graph down here. So this one goes up 10,000. So here's 5,000. So that's going to be like 22 something. 22. So the range of the function is about 10.5 to 22. So now in this situation, when we're figuring out the range of the function, it's the range of the situation that we're talking about, not just the mathematical formula. So don't get too bogged down in the math that you forget what the context is, because that's actually the whole point of math, is to help you in the real world or in the physical world to explain things. So compare the function's average rates of change on the intervals 50 to 200, 200 to 400. What do you conclude? So the function's average rates of change on the intervals 50 to 200 and 200 to 400. So remember, average rate of change is the change in x over the change in y. So this is a terrible graph to see it on. So I just went ahead and entered the values in for us. So we can see on the interval 50 to 200, it's going to be 13.5 minus 10.5 over 150. I would have just either turned that into a decimal or left it as a fraction, which is fine. But then when they do this one over here, a decimal over a fraction, that's weird. That's so weird. You will typically not see numbers like this in the real world. You'll either see them in a fraction or just straight decimal. Anyway, so then same thing on the interval 200 to 400, average rate of change is about this. The point here is that the rate of change decreases as the diameter increases. So if we look at the graph, as the diameter gets bigger and bigger, yes, it still increases, but it doesn't increase as much. So that's the whole point that they're trying to make there. So compare the commonly used formula with an alternative. So this is a function that amateurs use, apparently. One amateur astronomer used empirical data, gathered the survey of other amateur astronomers, and he found that amateur astronomers typically have the diameters from 50 to 600. So in this equation, which is labeled in red here, your domain is going to be 50 to 600. So what is the approximate range of the second function? So 50 to 600, No, we're not doing that. So I have both of these graphs labeled over here. And so let's see, this is our first one, and this is our second one. So the black one is our second one. So we can take that one off. We're going to go ahead and zoom out a little bit because we need what? 200, no, 50 to 200? 50 to 600. So we can check 50. 50 is 11.9. We'll say 12. I'm just going to go ahead and write that down on the screen so that I don't forget it. So now we need 600. $16.7. So what do we got here? At a minima, okay, for the domain, what is the approximate range of the second? So we said 12 to 16.7. So again, that's not doing the domain of the actual function, it's doing the domain and range of the real world situation. So it says identify the range of the second function if you let the second function have the same domain as the first. So remember, the first was from our professional telescopes. So that went from, well, what was it? So it went from 50 millimeters to 10,000 millimeters. So identify the range of the second function. So that's the amateur function with the domain 50 to 10,000. So if we go back to our Desmos or our graphing calculator, excuse me. So this is our second function here. So at 50, we'll call that 12. 12.0. And then 10,000. There's 1,000. 10,000, 22.1. So it's going to be, oops, 12.0 to 22.1. What? The domain is 50, so let's double check that. Did I put 12.0? Maybe they want like 11.9. Okay, that's a bug because they're giving me the answer and that was 12.0. So we're just gonna move on. So let's see here. Compare the ranges of the first and second function if you let the second function have the same domain as the first. Okay, so our range up here is 12 to 22.1 of our second function. So I'm going to have to write this up down. So our second function has the range of 12.0 to 22.1. So that's an interval. I should put it in interval notation. And then the first, again, this is the professional one, is 12.0 to 16.7. And that one is in interval notation, just to show you. So the two ranges are similar, I guess. Are similar. Oh, wait. Yeah, I would say they're similar. This suggests that the second function could be applied to the telescope with the diameter greater than 600 millimeters. So, okay. Both functions are increasing functions because the second function's graph, the red line, lies, let's check, above the first function's graph, the domain 50 to 600. The second function gives, oh my gosh, the second function's graph of the red line lies above the first function's graph on domain that the second function gives greater limiting magnitudes than the first function does in this domain. Functions give same limiting magnitude of about that when the diameter equals 14,700. So let's look at that. Let's see if their picture helps us. 14, close enough, 22.8. Which is greater diameter than its largest optical telescopes. So there you go. So that was kind of a weird, convoluted example, but it's just a matter of comparing the two functions together. All right, that was lesson 9.2. Try out those examples. I think you'll probably get a better understanding from the Check on Learning examples because I know some of that stuff was a little confusing when getting down to the domain and range. So check it out. I'll see you there.